We were in the middle of discussing spinors, and we had got as far, some things I'll just tell you and not prove. Not too many of them, I hope. Simply because it will take too long for us to do it. So we had got as far as defining the covariant derivative of the frame field. And this was del A of E B mu equals del A of E B mu plus gamma B A C E C mu plus omega mu nu A E B nu. This is supposed to be equal to 0 for our convenience. So that it's basically the same thing as demanding a symmetric metric connection. So if you think about this, you can turn this formula around and use it to determine the spin connection, omega. And the way to do this is to multiply the whole expression by E rho B with both of your indices downstairs. So it will read 0 is equal to E rho B del A of E B mu. So there's not much you can do with that. Plus E rho B gamma B A C E C mu, and there's not much that you can do with that either. But the last term you have an E omega mu nu A E B nu E rho B. So this thing here, this combination, is delta nu rho. So that means that you can now write out a formula for the spin connection. So you can just simply say, well, omega mu rho A is equal to minus all the other terms. So it's minus E rho B dA of E B mu minus E rho B gamma B A C E C mu. So that's something that you can actually calculate if you ever need to do that. So that is how to evaluate the spin connection in practice. Presumably many of you are going to Gary Gibbons's course on differential geometry. No? Oh, all right. I will not say what I was going to say then. Like any connection, you can define a curvature of a connection. So let's define R mu nu C D to be del mu omega nu C D minus del nu omega mu C D plus omega mu E C omega nu E d minus omega nu e c omega mu e d. That's right. So it's the same thing with mu and nu swapped round. So this thing has some symmetry properties. It's anti-symmetric under the interchange of mu and nu, and anti-symmetric under the interchange of c and d. So at the first sight, this thing doesn't look like it's got anything to do with a conventional Riemann tensor. However, a miracle is that. If you take R mu nu CD and you turn these first two indices into space-time indices using the frame field, that is to say, you take this object E mu A E nu B R mu nu C D. This is equal to the conventional Riemann tensor. That is a consequence of having defined the spin connection this way, or alternatively, it's a consequence of choosing the covariant derivative of the frame fields to be equal to 0. You didn't have to do that, but if you do that, then this is a nice identity, which means that computing things from the frame fields via the spin connection, or computing things from the Christoffel symbols, is the same thing. If you wish to prove this result, it is obvious how to do it. You can just substitute in the formula for the spin connection here, and then each time you see the spin connection you can substitute this in, and you'll discover all the terms involving grad E cancel out. So it's a conventional thing. I don't recommend doing this calculation. It isn't very nice. My guess is that Gary Gibbons did it, which is why I asked. No? Did he introduce forms? Then he did it. Maybe he didn't tell you he did it.
If we hadn't set this to 0, then we would have gotten some different tensor?
Yes.
At the end of the day?
Yes.
So given our metric and our manifold, we have our normal Riemann tensor, and we set up a frame field, we can set those differently. We can get a whole class of associated Riemann tensors. Indeed
you can, and indeed there's a whole book about it, written by a man called Schouten in the 1920s or so, called Ricci Calculus.
Okay.
I don't recommend reading that either. So now, what we're really trying to do is to find a way of describing the covariant derivative of the spinor. Maybe I should say something else about this business of the curvature. For those of you who have done differential forms, right, hands up those who know about differential forms and computations of curvature. Okay. Some dispute there about whether you know it or not. So, so if you're using differential forms, one thing that you would have constructed is an orthonormal basis of one forms. If you don't know about differential forms, ignore what I'm going to say. And these you probably called E mu. And these are the same things as E mu A dxa, where E mu A are the frame fields. You probably then decided that Cartan's first equation was 0 is equal to dE mu plus omega mu nu wedge E nu. Is that true? If you have done that, then this you call the connection 1 form, and it's related to the spin connection by omega mu nu a dxa is omega mu nu. And lastly, I should call it Cartan's first equation. I would have called this Cartan's first equation of structure, but I have no idea what he called it. He may have said that this was a torsion 2 form, but in general relativity the torsion is 0. I'm only guessing what he might have said. And lastly, he would have defined the curvature 2 form to be R mu nu equals d of omega mu nu plus omega mu rho wedge omega rho sigma. And the curvature 2 form is related to this curvature by R mu nu equals 1/2 of R mu nu a b dxa wedge dxb. That's the same formula. So he did not tell you that this is the same thing as the usual curvature tensor, but simply assumed it at a rough guess. I don't know that for a fact, but it's just a guess on my part. So, covariant derivative of spinors. Well, what we would like to define is an object del A acting on psi. Psi is a spinor, so we would like this thing to transform like a space-time vector times a spinor, simply by imitating what we have done for the covariant derivative acting on tensors. If you go through this calculation, you will say that the first term is that, and that does not transform in the correct way under local Lorentz transformations, and there is a correction term that you have to add. I will tell you what the correction term is, but I will not prove that it does what you want. It is 1/2 omega, sorry?
You said 1/2 quarter.
1/4. Mu nu a gamma mu nu acting on psi, where this thing is the commutator of 2 gamma matrices with a factor of 2 in it. So that is a formula for the covariant derivative of a spinor field. You can prove that it transforms like a spinor, but you have to go through the usual kind of manipulation involving doing a Lorentz transform and a coordinate transform to do that it does the right thing. I'm not going to do that. It works in exactly the same way as it works for vectors and tensors, so it's not very illuminating. If you wish to see somebody doing it, you can look in the book of Weinberg, where it is done in extreme gory detail, but watch out for sign mistakes. Or at least in my edition, watch out for sign mistakes. Later editions may be less buggy.
The problem with Weinberg is that when the signs are mistaken, the conventions are so odd.
Well, the conventions are variable. That is to say, the section on cosmology uses different sign conventions to the bit about relativity. So you have to be extremely careful. Probably nothing's actually wrong, just confused.
Just didn't read that paragraph.
Right. So, you can, of course, now ask yourself, what is the analogue of the Ricci identity for spinors? That is to say, calculate del A, del B minus del B of del A acting on psi. You can sort of see right away what it's got to be. This thing takes the derivative of the covariant derivative. Obviously, when you have partial derivatives, those terms will disappear because partial derivatives commute. But you'll end up with taking the derivative of this thing here. The result is that you will end up with 1/4 of R A B mu nu gamma mu nu acting on psi. That brings us to an interesting point concerning supersymmetry. How many people are going to the supersymmetry course? Right, lots. Good. You will not like this. Let's contemplate what happens if you want a constant spinor. A constant spinor of the type that is associated with global supersymmetry must obey del A epsilon equals 0. You cannot always satisfy that equation because this implies that del A del B epsilon is equal to 0, and that implies that RAB gamma mu nu gamma mu nu epsilon is equal to 0. And that tells you that curvature is in general an obstruction to having a covariantly constant spinor. We can do a little bit more about looking at this equation later on. Roughly speaking, if you have curvature, you can't have covariantly constant spinors. The reason that that's important for supersymmetry is that if you believe in supersymmetry, you start off by saying you have a constant spinor with which you generate supersymmetry transformations. So that means that if you believe in gravity and supersymmetry, you will have to believe in supergravity, where you make the spinors depend on their positions in space-time. So if you think that you're going to discover supersymmetry at the LHC, you can be certain you are going to discover supergravity later on. That's my view on the subject. Now, I think the useful thing to do now is to look at examples of a covariantly constant spinor, and let's do this in Minkowski space. So let's take Minkowski space in our favorite coordinate system. Obviously, if we have flat space, this thing is 0, and there is no obstacle to finding covariantly constant spinors. It's nice to do this in polar coordinates. You could do it in Cartesian coordinates, in which case it's kind of obvious what the answer is. The spin connection vanishes, and so you just simply get del A of epsilon equals 0. But it's much more instructive to do this in polar coordinates. So the metric on Minkowski space, I will choose to be minus dt squared plus dr squared plus r squared d theta squared plus r squared sine squared theta d phi squared. So the first thing I have to do is to choose a set of frame fields. E mu A. Now, it is kind of obvious that I'm going to have a slight problem here, because if I want to write out a frame field, I have to decide which is a Greek index or a Latin index when I've given it a number. So I will adopt the convention that if I've given an index a numerical value and I've underlined it, it's a tangent space index. Now, of course, I'm going to choose the frame fields. You can choose the frame fields to be many different things. You can't say, the frame field is this. It's ambiguous up to local Lorentz transformations. So it's like choosing coordinates to describe something. It's often best to simply pick the simplest possibility in practice. So recall that the metric tensor GAB must be equal to EA mu, EB nu, eta mu nu. So if we want to describe this metric up here, the simplest thing to do is to take E naught naught, underlined because that's a tangent space index, to be equal to 1. Then you can see that I get G naught naught equals minus 1. Here you'd have E naught 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 eta naught naught, which is minus 1, so you end up with minus 1. Similarly, I can choose E1 1 to be equal to 1. I can choose E2 2 to be equal to R, and I can choose E3 3 to be equal to R sine theta. So really all I have to do to get the correct metric is to square that. That's really just because the square of the frame fields is the metric, although you have to interpret the word squared with a little bit of caution, because this thing is the Minkowski space metric, not delta. So that's a choice of the way in which I'm going to do things. That leads to a spin connection. I should say all other components vanish. Of course, that would be helpful. Now you calculate the spin connection from this form. Remember that omega looks something like EDE and then a gamma EE term. I won't write that out in detail, we've already written it out once. And if you do that, you'll discover that 2 is equal to minus omega 1 3 3 is equal to minus sine theta. Omega 2 3 3 is equal to minus cos theta. And these are antisymmetric under the interchange of these pairs, so this is the same thing as minus omega 2 1 2. This is minus omega 3 1 3, and this is equal to minus omega 3 2 3. all other components vanish. I could have chosen more complicated E's over here, in which case I'll get a more complicated spin connection, because the spin connection is some complicated thing built out of the E's. This choice was deliberately made to make life easy for you.
Excuse me, what is omega? Is it index or the top line?
Top line. I just wrote omega looks like EDE and gamma EE from the formula that we had a little bit earlier. In fact, it's basically this formula here that we're talking about. If you want to calculate it, you see what you do is you take this formula and you look at EDE, that term, and gamma EE, which is this term. You have to put it in the indices, of course, but you want to think of something which looks like that, and then you just calculate it. The next thing that you want to do, if you want to look at solutions of this equation, is you're going to have to pick a representation of gamma matrices. That's because gamma shows up in the covariant derivative. You can, of course, pick any representation of gamma matrices you like, but I'm going to pick this one because it makes life easy. So gamma 0, I'm going to choose to be equal to. It's a 4 by 4 matrix which I will write as 4 2 by 2 matrices. 0, minus 1, plus 1, 0. The 1 there being just the unit 2 by 2 matrix. Notice that if I square that, I get minus 1, and you should not be surprised to see that gamma 0 is anti-Hermitian as a consequence. That always happens if you pick your signature to be minus plus plus plus, like I do. Then you need to pick gamma space. Those I will choose to be 0, sigma I, 0, where the sigma i's are the Pauli matrices. You can protest that this is representation dependent, what I'm about to do, and you'll be right. But if you want to do a practical calculation, you had better have a representation in mind, otherwise you'll become stuck.
Well, if we didn't set this covariant derivative of the Poincare fields to 0, we wouldn't have been able to compute the connection.
That's right.
So how do we have even begun, how do we proceed?
Well, if you don't have a formula for the connection, you will have a curvature built from it. But that's all you'd have.
Okay.
We've chosen, if you were just going to do ordinary general relativity, you always pick a connection which is a symmetric metric connection because it is convenient. Any other connection you could have picked is as good, except that you have to introduce other things to describe it. That's because the difference between two connections is a tensor. So, pick your favorite connection, pick the Christoffel connection, and the difference between the two must be a tensor. And if it's a tensor, you can describe it as some fundamental thing.
Okay.
So there could be, for example, torsion, or there could be a Weyl term, or there could be, what's it called? The thing that Schouten calls a Q. I can't remember what it's called. And the same is true for the spin connection. So it's no different. It's no different to what you usually do. And in fact, in supergravity, you have to change this ever so slightly, which is why we're not going to bother to teach supergravity because it would be rather complicated. My Pauli matrices, just for reference, are 0, 1, 1, 0. Sigma 2 is 0 minus I, 0. Sigma 3 is 1, 0, 0, minus 1. And as a consequence of that, you will notice that these are Hermitian, and therefore this is Hermitian. Now you substitute this in an explicit differential equation for epsilon, if you want to solve del A epsilon equals 0. With my representation, you will discover that epsilon is equal to. Now, if you look at the third example sheet, you will discover that I set an example to verify what I'm about to write down. I think it's right. I don't think I've got any sign mistakes in it. E to the I theta over 2, arbitrary constant e to the I phi over 2, minus an arbitrary constant e to the minus I phi over 2, e to the minus I theta over 2, same thing, that should be a plus. A, B, C, and D are complex constants of integration. The very first thing that you are likely to have noticed about this expression is something at first sight is a little bizarre. Phi is a polar angle in this coordinate system, and therefore, if you draw a picture of what's going on, so constant R is a sphere that looks like this. Here is a symmetry axis, and phi is a rotation that takes you round like that. So, if you send phi to phi plus 2 pi, you end up at the same point that you started off from. But each of these functions here will change sign. So epsilon is not single valued under rotations. But rather double valued. This should not give you sleepless nights. That's because you think of representations of the rotation group SO3 as being vectorial, and of course a spinor is not a representation of the rotation group, it's a representation of the cover of the rotation group, which is SU2. That's a double cover, reflecting the fact that this thing is not single valued but double valued. So you should not be alarmed by the apparent double valued nature of epsilon. It's not apparent, it's real double valued if you consider it as being a representation of SO3, which it isn't really. There are people who are more flexible than I am who can demonstrate that SU2 is a symmetry of the real world and not SO3, but I can't do it. Jake can, it would seem. you can get him to show you later. Now, so why did I bother to do all of this? And the answer is that for some things you need spinors. For roughly 50 years, people searched for proofs of the positive energy theorem based entirely on vectors and tensors. They did not find one. But it is easy to construct one involving spinors. So this is how it works. Here is space-time, and I'm going to consider just asymptotically flat space-times, and I'm not going to deal with things that contain singularities or horizons, although you can if you wish. So here is space-time, it is asymptotically flat. So out at infinity, you know that it approaches Minkowski space. Here is a spatial surface, a surface of t equals constant or something like that. It's sitting in space-time, and it will have a unit normal to it, TA, everywhere, and it will be time-like. If there is a metric GAB, which there probably is for our purposes, there will be an induced metric on this surface, HAB. HAB is equal to GAB plus TATB. Let's call this surface sigma. So, now the trick. Let's consider what is usually called the Witten equation. There is something vaguely ironic about this. The Witten equation sounds like an ambiguous title because it's not clear which Witten it is. Lewis Witten worked for a very long period of time on the positive energy theorem without getting very far. His son, Ed Witten, worked on the positive energy theorem for about 2 weeks and did get somewhere. The Witten equation, so it's the Ed Witten equation, not the Lewis Witten equation, is defined to be that. This is more or less the projection of the Dirac operator into the surface sigma. I need to have one piece of notation here. The piece of notation that I'm missing is that I have given gamma A space-time index, whereas in fact I've only defined it with a tangent space index. So let's cure that. Gamma A with a space-time index is defined to be EA mu gamma mu. And it will have, in order to be consistent with everything else, vanishing covariant derivative. You would be perfectly entitled to say at this point, why isn't it the projection of the Dirac operator into the surface sigma? There are two reasons. The first is that if it was, it wouldn't work, which is a very unsatisfying reason. The Dirac operator would be GAB gamma A dB epsilon equals 0. That's a Dirac equation. If you wanted to construct the Dirac operator in the surface sigma, what you would do is you would take HAB, gamma A in some three-dimensional sense, del B built out of H and its associated Vierbeins. So that's a three-dimensional Dirac operator, and you can immediately see that this is quite different to this one, or that one. This thing would involve something built out of H, but actually what you want here to make it work is something built out of G. So it isn't really the projection of the Dirac operator into sigma, but just rather like it. So that's not what we're going to be interested in, and indeed it does not work. So what does work? What you do is you know that out here, where the curvature is falling off, you can construct covariantly constant spinors. So near spatial infinity, you can construct constant spinors. So out near infinity, you know that these things will satisfy this equation because del B epsilon is equal to 0. What is less obvious is that you can solve the Witten equation everywhere.
Are there any topological caveats for being able to construct constant spinors at infinity? I mean, you've excluded horizons and singularity, but are you also excluding non-trivial topological structures?
Well, I think that if it's asymptotically flat, I'm thinking of infinity as being, roughly speaking, R cross S2.
So something like fours.
Nothing weird. You can,
Asymptotically flat.
yeah, asymptotically flat in some global sense. You can undoubtedly relax that condition if you wish, but you are likely to get yourself into trouble if you try that. So there's a whole collection of wrong papers where that was not done properly, and I'm glad to say I wasn't the author of one of them. I wasn't the author of any of them, actually. So you want to solve the Witten equation in such a way that the solutions are asymptotic to the constant spinors. Now, if you just think about differential equations for a bit, this is a first-order differential equation, and here, and what you're asking is, can you solve this equation subject to this boundary condition? And roughly speaking, the answer is yes, if you can construct a Green's function to this operator. So that's basically the condition that is required to make this work. So everything I say is based on that particular requirement. What then happens? So let's pick ourselves to get B, C, and D equal to 0 and just have A. So that's an example of a constant spinor. So epsilon 1 looks like e to the I theta plus phi over 2. Epsilon 2 is e to the I minus theta plus phi over 2. Epsilon 3 and epsilon 4 go to 0. What is the first correction in powers of 1 over r? You will discover, unsurprisingly, that if the space-time metric looks like the Schwarzschild metric, if you like, that's just saying there is a Newtonian gravitational mass, then you will discover that these things are modified into 1 minus 2m over r plus higher order stuff in r. This one gives me 1 minus 2m over r, also plus higher order stuff in r. And that's all. So,
wait, you started off the argument with saying that there were no singularities, but
I said Schwarzschild like at infinity. I haven't told you about anywhere else.
okay.
Doesn't have to satisfy the vacuum equations.
Okay.
So all this is really saying is that there is a Newtonian mass. That's all I've required from that. You can deal with things like black hole metrics, but you can't deal with things which are singular. So if you stare at this formula, you will realize that this, of course, looks very much like what you got from killing vectors when you looked at Komar type formulae. You ended up with 1 plus a correction term involving the mass if you looked at the components of the vector. So that should give you the idea of finding a different formula for the mass. So here is a different formula for the mass. Here is epsilon. So let's invent a quantity which, when integrated out at infinity, gives you the mass. I'll call that vector x. It's going to be epsilon dagger HAB del B epsilon. You can see that that's more or less the right thing, because if you look at this formula, you know that when the covariant derivative out at infinity hits this term, 1 times e to the I theta plus phi over 2, you get nothing. But that's because it's constant out at infinity. Now let's look at this other derivative. This thing could have an r component. If it's got an r component, you're going to differentiate with respect to r. So the d del epsilon r component is going to look something like 2m over r squared e to the I theta plus phi over 2, 2m over r squared e to the I minus theta plus phi over 2, 0, 0.
XA, what is that epsilon plus or dagger? Or?
It's epsilon dagger. Let's continue with this calculation. Out near infinity, HRR looks something like 1. Epsilon dagger is equal to, ignoring the sub-leading terms, it will be e to the minus I theta plus phi over 2, e to the minus I minus theta plus phi over 2, 0, 0, plus higher order stuff in both cases. And so epsilon, so this vector XA has an R component which looks something like this times this. Well, that's going to be a 1, and you'll get 2m over r squared from that term, and another 2m over r squared from that term and that term. So the total is 4m over r squared. So that's xr. Now you could invent an integral over infinity, exactly the same way that we did for the Komar formula. you integrate over a sphere at infinity, Ta xb ds ab, and that will give you the mass. Ta is, of course, the unit time-like vector out at infinity, so that this thing has a 0, so that means that that's a 0. This will have an r component, so you have to have ds 0r. So if you just calculate this object out near infinity, Ta looks like 1, 0, 0, 0. Xr, the only component that you're interested in, is 0, 4m over r squared, 0, 0, plus higher order stuff, I suppose. DSAB, DS01 is equal to minus r squared sine theta d theta d phi. The minus has come from lowering this 0. Remember that this thing looks like DSAB is supposed to look like TARB times the induced metric on the surface, gamma to half d2x. Hence the minus sign. So this thing is, putting it all together, integral Ta xb ds ab is going to be equal to minus r squared sine theta d theta d phi a 4m over r squared integrated over the sphere to infinity, and that's equal to minus 16 pi m. So integrating up this thing gives you the mass. We have made one mistake. There should be a 1/2 there, which means there should be a 1/2 here, which means there should be 8 pi m. So the mass is equal to minus 1 over 8 pi integral of Ta xb ds ab over the sphere at infinity, which I will call I0. This expression has remarkable positivity properties, unlike things made out of vectors. I will prove that on Friday. You better stop. It looks like Michael Green is getting impatient.